Okay, so the next part of our review, vectors. We've done a little bit on the basics of vectors, and so we're just going to quickly go over what we did, what we covered, and make sure we understand what's going on. Everyone, I hope you're enjoying my shirt there. That's just for Mr. Fletcher, that one, and given that I'm doing a physics-related topic of vectors, I thought I'd just make sure everyone enjoyed that little joke at his expense. I know I didn't, I know he didn't. That's the main thing, isn't it? No, he's a good sport. All right, what are vectors? There's 30 seconds of your life you're never getting back. Vectors, what's the key feature? They are quantities with a magnitude and a direction. Magnitude and a direction. So we talk about the speed is how quickly something is going, but the velocity, that's a vector quantity, it's the speed it's traveling at in a particular direction, and that can become very important. We gave some examples of like when we're trying to swim across a river and the current's going one way and we get dragged along, or flying to Perth and back, and how because of the winds we actually take different amounts of time to finish that trip, even when we feel like we're going at the same speed, and when our airspeed is the same, our actual speed over the ground is different. How do I represent vectors? Two ways we looked at. Lines with an arrow indicating the direction. The length of the line, that indicates its magnitude or its size, and we'll talk about that again in a little bit. That's a vector there. I might want to call that vector A. Remember, there's lots of ways of writing vector A like that. The book sometimes says like that. You can actually do A with a tilde underneath it as well. All of those would represent vector A. Let's not get too hung up about that. As we do these for 2 years, you're going to get very comfortable with all the different notations, and it's not a problem. Quantities with a magnitude and director, that's the important bit. The other way we can write vectors, if it's a two-dimensional vector, we can have the change in the horizontal direction and the change in the vertical direction, or the change in X and change in Y. Remember how far across we go, how far up we go. We were trying to get from the origin to the point 4, 3, I think it was, so it would have been 4 across and 3 up. So we can use vectors like that. We also learnt about little unit vectors or component vectors we could have. If I had the vector 3, 4, so it's now going 3 in the X direction, 4 in the Y direction, or 3 across and 4 up, if you want to think about it that way. That's the same as saying 3 in the little I direction and 4 in the J direction. We talked about how I and J are unit vectors in the direction of X and Y respectively, and just by combining those, multiples of those, we can end up anywhere. When we went to 3 dimensions, we have Z, IJK, and the Z-axis, a K is a unit vector in the direction of the positive Z-axis. We'll get used to using all of those. Not too much of a big deal. What else did we cover? When are vectors equal? This was pretty easy. I don't even need to stick some space in there. What do they have to do to be equal? They have to have the same magnitude. So the magnitudes are equal. And what's the other thing? The directions must be the same. The same direction. What they do not need to have is the same location. So these two vectors would be equal, assuming that I've drawn them perfectly equal in length. Looks like the second one was marginally longer, but you get the idea. So long as they have the same direction, same length, they are equal vectors, whether or not they are in a different location in the plane. What's the negative of a vector? Let's say I have vector A, and vector A is quite inspirationally drawn, just like that. What would negative vector A be? Well, it would be the same length, same magnitude, in the opposite direction. Pretty straightforward, that one. The negative of vector going in the opposite direction. Again, if I had vector, let's not use J, let's make it something different. Vector capital M. And vector capital M, this time I gave you as a component vector, -2, 4. Well, therefore, negative vector M is going to be 2, -4. The negative of the vector just means I would make the components negative. That would work the same way. How do I add vectors? Pretty straightforward procedure here. If you have one vector, there's vector A, here is vector B, and I want to add those two vectors together. all I would do is place the first vector down, and then the tail of the second vector starts at the head of the first vector. There's vector B. That would be how I add them. The resultant vector, from the start of the first one to the finish of the second one, that would be called vector A plus B. Not too complicated, is it? What about finding the magnitude of a vector? How do I find the magnitude of a vector? Let's have one going the other way this time. How do I find the magnitude of that, given that I might know its components? Let's say this is the change in y, the change in the y direction. This is the change in the x direction. Well, what sort of shape have I got there? I've got a right-angled triangle. When you see a right-angled triangle, you think Pythagoras. So the magnitude, let's call this vector n. Why not? Vector n. The magnitude of vector n, so the magnitude's indicated by those absolute value signs. The magnitude of vector n, I just apply Pythagoras' theorem. It's the change in the y coordinates. And of course, Pythagoras' theorem says we have to square those, plus the change in the x coordinates. And I square those, and then of course I square root it to find just n rather than n squared. So, pretty simple, pretty straightforward. Multiplication by a scalar, what does that do? Haven't left myself a lot of room there, but that's okay. Let's have a vector, just a nice short one. That's vector c. How would I write vector 4c? So multiplying vector c by a constant, well, I just take vector c and place 4 of them end to end like that. So it is now 4 times the length. Remember, the magnitude is represented by the length, so multiplying by a scalar just changes the length, not the direction. Finally, the vector between 2 points was the last little bit that we did. So we considered the case where we had 2 points in the plane somewhere. Here is point A, so it was found by vector OA. There's point A. This is vector from the origin to A. That's the other way we can write them, from a point to another point. Here is vector B. So I could have vector OB there in that direction. So we've got the vector from the origin to A and the vector from the origin to B. How do I find vector AB? We know what it looks like on here. I simply go across from A to B. How would I find that? The same way I normally do. It's sort of like a gradient, isn't it? Rise over run. So do the change in the vertical components and a change in the horizontal components. How else can you think of that in this one here? Well, I'd have to go back along OA and then forwards along OB to end up with the same result, wouldn't I? So I could write it in any number of ways, including these. So I could go backwards along OA and then forwards along OB. Well, it's just as easy to write that in the other way around. I could go forwards along OB and then backwards along OA. Let's say this point B, I'm very creative, and I know that it's made up of the components B1 and B2. We're in a two-dimensional plane, so B1 is the horizontal change, B2 is the vertical change. This point A, it's made up of two components, A1 and A2. A1, the horizontal distance, A2, the vertical distance. I can rewrite these in terms of those component vectors, can't I? Those column vectors. This is B1 and B2. OA is A1 and A2. Oh, what does that mean I can do? I can just find B1 minus A1, the difference between the x coordinates, and then B2 minus A2, the difference between the y coordinates or the y components of the vectors, and that will give me the components of vector AB. Wow, we covered a lot, didn't we? We really need to spend a couple of days just hammering down some of the problems from the textbook, trying some, seeing how we go, getting stuck, asking about them, helping each other out, moving on. If we do that, we're going to find that we can do all of this maths pretty easily, and it'll be sinking in, and we'll be starting to get it into our long-term memory so we can't forget it. More importantly, trying to understand exactly how everything works. If we understand how it works when it comes to our exam at the end of next year, we're not going to have any trouble at all. It's going to be pretty easy. That's the plan. Let's see if it works. Keep up the good work, guys. Cheers.